Australia's Uranium Opportunities by Keith Alder. Recorded by Logan Smith with the permission of the Alder family. Chapter 17. The AAEC Centrifuge Enrichment Program. One of the first proposals for new research made to the Commission when I was appointed Director of the Research Establishment early in 1962 was for a modest program on the gas centrifuge for uranium enrichment. The proposal originated from one of our senior metallurgists, Mr. F. L. Frank Bett, and myself. Frank later became head of the Australian Safeguards Office, responsible for nuclear non-proliferation matters. The reasons we put to the Commission were accepted, but the proposal was not. The chairman, then Professor Baxter, said he had sympathy for the idea, but that even if we tried to keep it secret, it would leak out and be misunderstood internationally. In other words, people would assume we had an interest in producing enriched uranium for making bombs. Incidentally, this supports my statement, Chapter 1, that Baxter did not at any time propose work directed towards atomic weapons. He did not want our image tainted by such accusations. However, the Commission acknowledged the potential of the centrifuge method of enrichment and particularly its suitability for small plants, and reported its interests in its 1960-61 annual report. The main reasons we put forward in this early proposal were the need to develop facilities to produce our own research reactor fuel, and fuel for the municipality of the radiation experiments we foresaw in connection with the high-temperature gas-cooled reactor research program. We were already having difficulty obtaining fissile material for this purpose, and we expected these problems to continue. In retrospect, our enthusiasm was, to say the least, naive. We really had little idea of the technical difficulties presented by the gas centrifuge, but in any case, the proposal lapsed until 1965. In that year, I raised it again with the chairman, pointing out that the new discoveries of uranium in Australia and the concept of processing at home to add value to minerals for export gave an additional good reason to start such a project as a long-term investment. He agreed, and a formal proposal went to the next Commission meeting and was approved. But the decision was to keep the project secret, for the time being at least, to avoid, if possible, any allegations of intentions to develop nuclear explosives. We were thus very careful indeed in who was selected to work on the project, and I interviewed everybody selected to sound out their willingness to work under conditions of secrecy. This was something we had never had before, despite popular and media theories that much of the Commission's work was secret. This meant, of course, that they could not publish their work, which would affect mainly the professional staff. But the other main effect, for everyone involved, would be that they could not discuss it with anybody outside the project, not even their families. Initially, a small team of only 6 persons started the project in a limited-access basement laboratory under the Health and Safety Building. We had a chemical engineer to look after the manufacture of uranium hexafluoride, which is the gaseous feed for centrifuges, and a mechanical engineer to start the development of the centrifuge. They were assisted by 4 of the best technicians we had. It did not take long to demonstrate that there were many technical problems to solve. The type of gas centrifuge we chose to develop had run at very high speed, over 1,000 revolutions per minute, in a low-pressure atmosphere of uranium hexafluoride. The rotor has to be made of material with a high strength-to-weight ratio, and be compatible with the working gas. It has to be driven by a special electric motor, itself made of materials with these characteristics. It has to run on a bearing or bearings of low friction, using a lubricant which is also compatible with the gas. And to be successful in economic terms, it has to be inexpensive to make and reliable enough to run for years without breakdown or maintenance. The critical design parameters for good separative performance are the peripheral speed and the length. In order to get the separative power, the number of separative work units per annum per machine, high enough, the rotor has to run at supercritical speed, i.e. above the speed at which it tends to vibrate in a mode determined by its length and the properties of the rotor material. Getting these rotors up to speed through the various criticals requires some clever engineering of bearings, dampers, and rotor design. And once into the supercritical regime, they have to spin at supersonic wall speeds for years. The approach to these problems by the three partners in the European tripartite companies Urenco-Centec involves relatively small, low-cost machines which are designed to run for years and then be discarded. Another approach, adopted by the USA and later abandoned, was to build very large centrifuges which were much more expensive but could be taken out of service when necessary for maintenance or major rebuilding. I will enlarge on this in describing the activities of UEGA. See Chapter 18. We called the centrifuge group the Mechanical Development Section. It was expanded fairly quickly, still by careful selection and with choice of refusal by those invited to join over the next 2 years. We began construction of a new building to house the growing program, which was named Project Whistle in the early days because of the sound from the high-frequency electrical supply to the synchronous motors driving the machines. One early worry was the danger of flying fragments when rotors disintegrated, which was not unusual in the early days of the project. We built small concrete blockhouses in the laboratories in which to run the experimental machines, and tested whether anything could get out through the labyrinth entrance by firing a high-velocity rifle in one during silent hours one weekend. The Commonwealth Police on the gate were very perplexed by this exercise. Special approval had to be granted to bring a firearm onto the site. Later, cabinets with half-inch thick steel walls were built to house the experimental models. The Commission decided in 1967 to announce in its annual report that it had a modest program of research and development in the field of gas centrifuge enrichment. Then, the chairman, Sir Philip Baxter, announced the project in September 1968 at the 12th Annual General Conference of the International Atomic Energy Agency in Vienna. Subsequently, on our way home, he and I discussed it with the US Atomic Energy Commission in Washington, advising them that we intended to retain the secret classification for the details of the work, a decision which pleased them. The level of effort devoted to centrifuge research was increased considerably from 1967 onwards, and particularly in 1969 to 70. The return of staff from the United Kingdom study on the SGHWN reactor enabled some redeployment, and a senior engineer, Mr. D.R. Doug Eberling, was appointed head of the growing mechanical development section. By 1971, considerable progress had been made in solving the problems of bearings, dampers, motors, and alternative rotor materials, and in the design and operation of individual machines. It was then possible to begin construction of the first laboratory-scale cascade, which was later featured on the front cover of the AAEC Annual Report of 1975-6. This used machines with aluminium alloy rotors running at subcritical speeds, but at the same time other materials were being developed, including alloy steels and filament wound composites. Australian industry was also being brought into the project, with the setting up of premises for manufacture of components and later complete centrifuges. The Commission reported in 1971-2 that the centrifuge research and development was now one of its major research projects. The project underwent a major review in 1974, following which the Commission was able to advise Rex Connor, then Minister for Minerals and Energy, that it was confident of continuing independent centrifuge development to the stage of a commercial plant. The Minister announced this in Parliament in April 1975. The enthusiasm displayed by this Labour government was somewhat ironical in the view of later developments under a different Labour administration. The annual report of the AAEC for 1975-76 outlined the research program on centrifuge enrichment in some detail, stating the objectives to be 1. To provide the technical basis for the option to construct and operate a commercial plant in the 1980s based on Australian technology if overseas technology is not available on the required timetable, or if terms and conditions of access are not acceptable to the Australian government and industry. It involves the development of individual machines in collaboration with industry and the operation of machines in experimental cascades. 2. To assess thoroughly any proposals for the licensing of overseas technology based on detailed knowledge obtained in the technical program. By this time, confidence was high, and the Commission thought it appropriate to give some ballpark figures on the characteristics and performance which had to be attained to enable a centrifuge plant to compete with gaseous diffusion technology. The example given was a machine giving 5 separative work units, SWUs, per year, a life of at least 5 years, and a cost per machine of less than $500 in large-scale production. We announced that enrichment on a small scale had been achieved in November in 1968, and from 1971 onwards, the AAEC had collaborated with a number of industrial companies in development of materials and components, and consultants had assisted with design and cost studies on conceptual plants. The project continued to expand and by 1977 had been reorganised into the Centrifuge Enrichment Project Division, CEPD, at the research establishment. It was then the largest of the research divisions. Doug Eberling was the chief of division with 3 section heads, Mr. J. John Price, Centrifuge Unit Development Section, Mr. K. S. Kevin Turner, Cascade Development Section, and Mr. D. J. Don Mercer, leading the Separation Performance Section. In addition, the Materials Division of the research establishment was undertaking backup research on rotor materials including miraging steel and epoxy carbon fibre composites. By the end of 1978, the first experimental cascade using machines by an Australian company to the CEPD design was running and produced small quantities of uranium hexafluoride enriched to 3.6% U-235, about the maximum level required by water-moderated and cooled power reactors. That appeared to us to be a very significant development at that particular time, giving realistic optimism for the future of an Australian uranium processing industry. In Europe at the time, the Centec Urenco companies had begun operation of their first small commercial centrifuge plant. The French were building their diffusion plant, which earlier they had hoped to build in Australia, in southern France, and the Japanese had started construction of their first centrifuge pilot plant. We knew of the interest of all 3 in the possibilities and prospects of an Australian plant, because we had carried out joint studies with each of them, and met and talked with their people in many international meetings. The reason for this interest was not difficult to assess. The lure was the guaranteed long-term supply of uranium. While the French and one of the partners in the tripartite companies had their own sources of the raw material, it was certainly not on the scale of the Australian resources. The Japanese had no indigenous source and, looking to the future, saw attractions in Australia as a reliable supplier, and if we wished to sell upgraded product, so be it, and they would like a share of the action. For our part, we realised the gap that still existed between what we had achieved and a full-scale commercial enrichment plant. Although we had developed good single machines and could see substantial improvements ahead and learned to cascade them, we were still a long way behind the Centec Urenco consortium. Specifically, they had run and cascaded thousands of machines for periods of years, accumulating long-term cost, performance and reliability data which we did not have, and which would take a few more years to accumulate. So there appeared to be substantial technical and economic advantages in collaborating with them if a suitable deal could be arranged. and there would be other advantages too, in commercial terms, for they already had a marketing organisation and customers with confidence. There is no doubt that the government of the day agreed that uranium enrichment would be a worthwhile industry for Australia. The ministerial statement of January 1979, referred to in Chapter 16 above, outlined its attitude and the intention to press ahead with feasibility studies with potential collaborators. Also at this time, some interest was shown by several Australian companies in the prospects of uranium upgrading industries. We already had companies involved in the research and development program, but now the commercial prospects for the industry began to attract attention. In Sydney, Sir William Tyree of Tyree Industries assembled an interested group which we briefed at a number of meetings. They also made their own contacts overseas, with the US AAEC and with Urenco. Eventually, this group concentrated its studies on the first stage of the upgrading process, the manufacture of uranium hexafluoride, but did not proceed past a short pre-feasibility study. They seemed to be deterred by matters of security and government involvement in the protection of the technology of enrichment. Then, in 1980, another group of Australian companies formed a joint venture to undertake a pre-feasibility study to assess the viability of establishing a commercial uranium enrichment industry in Australia. This is described in the next chapter. In the meantime, the AAEC's Centrifuge Enrichment Project Division, CEPD, continued development of single units and cascades. Means were devised to overcome the problems of driving machines at supercritical speeds, which give improved performance but impose problems with material strength and with destructive vibration as the critical speeds are passed. A major feature of these developments was the use of articulated rotors to obtain a high length-to-diameter ratio, giving more separative work per machine. In 1981, the Commission reported that high efficiency of separation had been achieved on the longer, higher speed rotors, and that most of the manufacturing techniques were now under deployment in industry. Also at that time, a consortium comprising Broken Hill Associated Smelters, 35%, British Nuclear Fuels Limited, 30%, Roxby Management Services, 30%, and the South Australian Government, 5%, announced a joint study of a conversion plant to make uranium hexafluoride in the Port Pirie area of South Australia. This was largely the result of a long campaign led by a former State Director of Mines, Sir Ben Dickinson, to bring a uranium processing industry to South Australia. By mid-1982, the Centrifuge project remained the major research and development activity at Lucas Heights, and its funding had been augmented by grants totalling almost $2 million from the National Energy Research, Development and Demonstration Council, NERDDC. Further progress had been made on more advanced rotors, and confidence was high that the project could lead to a successful commercial plant. At this time, nearly half of the Commission's research effort was being spent on the nuclear fuel cycle, and about half of this was on uranium enrichment, including a small effort on an alternative method using laser beams. Then, early in 1983, Australia had another change of government, from Liberal Country Party to Labor. Almost immediately, there began a series of major changes to the research program at Lucas Heights. The only ongoing work relating to nuclear fission would be that essential to support the operation of the research reactors, and to provide advice to government. All nuclear fuel cycle work would be scaled down, except that relating to development of SynRock, a method of fixing high activity level nuclear wastes, which, incidentally, Australia does not produce. And in particular, the uranium enrichment project began to be scaled down. The Commission stated that the future of the program is being assessed in the light of government policies regarding the uranium industry. A substantial reduction in staffing has already been made. In other words, the new government did not want any work to continue on uranium as a fuel despite the magnitude of the Australian resources, knowledge of which had continued to expand through the 1970s to 80s. Uranium was, politically, very incorrect. In announcing the scale down, and soon after the termination of the project, the AAEC somewhat sadly reported the success of its research in the following words. The program has demonstrated Australia's ability to design, build and operate enrichment cascades, was aimed originally at ensuring maximum Australian participation in any scheme for upgrading the product of Australia's large uranium deposits. The Centrifuge Enrichment Project Division was disbanded early in 1985. For a while, some of its facilities, in particular the Centrifuge Test Bank and the isotopic measuring equipment, were used for research and development on monitoring devices for enrichment plants, in work done for the Nuclear Safeguards Program of the International Atomic Energy Agency. This work was very successful. However, by February 1986, all work associated with enrichment by the centrifuge method had ceased. It is difficult to put a figure on what the whole project had cost because of the widespread nature of the effort at the research establishment and in Australian industry. But a guess of 2,000 man-years would not be too far from the mark. Plus, of course, the expenditure on buildings, equipment, stores, consultants, and outside contracts. All adding probably to something close to $100 million, and once again all scrapped because of political ideology. The clever country? Just what a disaster this represented for Australia will be clear from the next chapter of the story, because the CEPD, its program, its know-how and its achievements should have been a vital ingredient in setting up an Australian uranium processing industry. Such an industry might still eventuate in the long term, as I will explain later. But one of our major bargaining points, and of course our expertise to assess and specify the nature of technology to be obtained from overseas for use here, were lost forever, with the termination of the AAEC Centrifuge Enrichment Program and the disbanding of the CEPD. End of Chapter 17. Australia's Uranium Opportunities by Keith Alder. Recorded by Logan Smith with the permission of the Alder family. Chapter 18. The Uranium Enrichment Group of Australia. Early in 1980, 4 major Australian companies formed a joint venture, the Uranium Enrichment Group of Australia, UEGA, to undertake a pre-feasibility study to assess the viability of establishing a commercial uranium enrichment industry in Australia. The companies were the Broken Hill Proprietary Company Limited, CSR Limited, Pico Wallsend Operations Limited, and Western Mining Corporation Limited. Senior management staff of several of these companies had shown interest earlier in the prospects of the industry in Australia, and had been briefed by the Commission's staff. In particular, Dr. R.G. Bob Ward, Director of Research for BHP, was aware of the AAEC's program and international studies. He was a member of the Commission and its Deputy Chairman from 1968 to 75. And the Chairman of PICO, Sir John Proud, likewise had shown interest and had been briefed. There had been others too, included officers from AWA and ACI. The Commission provided technical assistance to UEGA, and a Commission officer, Alan Marks, was granted full-time leave to act as a consultant during the study, which took just over a year. The Minister for National Development and Energy, Senator the Honourable J.L. Carrick, announced on 3rd June 1981 that the pre-feasibility study was complete and that UEGA was prepared to undertake a full feasibility study at its own expense. UEGA had identified centrifuge and chemical exchange technology, then being promoted by the French, as potentially suitable for Australia. The government authorised UEGA to undertake the study, subject to satisfactory arrangements being finalised with the foreign technology holder and the Commonwealth Government. This was necessary because then, and now, enrichment technology was and remains a classified subject. The study was expected to take over 2 years and to cost about $5 million. The government agreed that the AAEC would continue to provide technical advice to UEGA for the full period of the feasibility study. UEGA began commercial negotiations with potential overseas technology holders during the latter part of 1981. In the AAEC, we knew from previous contacts that there was interest overseas in the prospects of enrichment in Australia, but the strength of the reaction to the UEGA surprised us all. There was to be no problem in finding a technological partner. In fact, quite the reverse. The problem would be to pick the best in terms of the worth and potential of the technology, and the terms of the deal to bring it to Australia. A number of us from the AAEC were involved from the beginning as advisors to the UEGA in numerous ways. As I have described earlier in detail, we had carried out international studies with the USA, France, Japan, and the UK, German, Netherlands companies, Centrifuge, and in the process learned a lot about gaseous diffusion and centrifuge technologies. We had done market surveys of future supply and demand, and we knew the characteristics of the various nuclear power reactor types and their fuel requirements. We had our own in-house expertise on centrifuge enrichment, and we knew all the people overseas who would be involved in the negotiations by UEGA. Soon after the start of the full feasibility study, I retired from the AAEC in January 1982. I was invited immediately to become a consultant to the UEGA, and I agreed. And from that time until the end of the study, I worked part-time for the UEGA with a base in CSR premises in Sydney. Early in 1982, it became clear that the choice of technology for UEGA would be between two different centrifuges, the USA and the Centrifuge types, and the French chemical method, of which we knew very little at that stage. The French also made a very strong case for their gaseous diffusion technology as used in the Urodiff plant in the south of France, which the AAEC had studied in detail earlier. The French were so keen to work with the UEGA that they set up an office in Sydney with a full-time liaison officer, M. Michel Mézin, to promote their technology and expedite communication. And the Urenco people sent a team to Sydney early in 1982, led by Mr. Jack Parry, seeking to convince UEGA that their technology should be used in any Australian plant. The US AEC also sent a team to convince us of the merits of their large repairable centrifuge. This and the French chemical method were the only technologies offered which had not been studied in detail already by the AAEC. Accordingly, the UEGA board decided to send a mission to the USA to investigate the American centrifuge. The chemical method was considered of low priority, and it was not thought necessary to visit the UK, German, Dutch consortium as they brought considerable detail to Sydney. So in May 1983, I led a team of 4 from BHP and CSR on a visit to the USA to look at their centrifuges. This was a very interesting exercise. I had seen the US gaseous diffusion technology at Oak Ridge, the UK diffusion plant at Capenhurst, the French diffusion plants at Pierre-Latte, military, and the Urodiff civil plant. Also, the Urenco pilot plants at Capenhurst and at Almelo in Holland. But none of us had seen the US centrifuge before. Most of the developments in the USA was being done under contracts in industry, and we visited 2 companies building centrifuges and associated equipment. The Garrett Company in Los Angeles, and Goodyear at Akron, Ohio. And we had extensive discussions with officials of the US Department of Energy, DOE, in Germantown, Maryland, near Washington, D.C. It turned out the US machines were indeed very large and designed to be removed from service and rebuilt in the event of malfunction. From memory and our guesstimates, they were about 15 metres high and 3/4 of a metre in diameter. We were shown single units and small cascades in operation, but not the actual rotor. This was the big secret, not to be disclosed, even if we acquired the technology. The rotors would be manufactured in the USA and returned there, and the material and method of construction would remain secret. We concluded from odd remarks that it was a wound filament epoxy resin composite, but we did not know the nature of the filament. The need to be able to remove a machine from the cascade and return it after maintenance or rebuilding required the building to be very high with accurate crane access and very large in area to accommodate all the machines and sufficient space around them to give working room. The facilities for maintenance or rebuilding of machines were also on a very large scale. At Garrett, they used a building originally designed for large rocket manufacture and maintenance. The actual servicing of the machines was done on a production line basis, the line being called the gate line, with a number of workstations and the machines being moved on one place at a time to the next operating position. After long talks to the DOE people, one visit to Goodyear and two to Garrett, we had enough information to make an assessment of the likely economics of the US centrifuge compared with the European one. Most of the capital cost assessments were done by the two BHP engineers, who were experienced estimators. The conclusion was quite clearly that we did not believe the US centrifuge technology could compete with that developed by Centec Urenco. While we did not have detailed cost data for the centrifuges themselves, only ballpark figures given to us under that title, we could estimate the building and maintenance line costs, which put the economics out of competition. I might add that this conclusion did not endear us to our American friends, when they had it conveyed to them later. But not very long after that, the US DOE abandoned its centrifuge program. A large production plant based on that technology was to have been built in Paducah, Kentucky, but it was never built. The French pushed very hard for us to reconsider their gaseous diffusion technology as used in Eurodiff. But a principal problem was that it had to be used in a large high-capacity plant at the outset, which raised marketing and early cash flow problems, whereas the European centrifuge could be used in small plants which could grow as the market justified. The French chemical plant was a relative unknown, and we were provided with a fair amount of detail on the process. But it had never been used on a commercial scale, and there were many questions to be answered during further research and development, so it was not regarded as a serious contender. One interesting aspect of the chemical process was the impossibility of using it to produce highly enriched uranium because of criticality problems. In other words, vessels containing highly enriched uranium solutions would go critical and become nuclear reactors, so the process had considerable attraction in terms of nuclear non-proliferation. Thus, by a process of elimination, UEGA concluded that the best prospect for Australia would be to enter into an agreement with the European tripartite to make it a quadripartite with Australia as the fourth partner, which would include participation in the ongoing research and development, with the AAEC Centrifuge project as the starting point for the Australian side of the R&D. We considered that the AAEC could most likely contribute to the development of better machines by pooling its knowledge with the others, as they had done already, and this idea seemed acceptable to the tripartite representatives. Meanwhile, UEGA had spent considerable time and expense on its own supply-demand studies, assisted by the AAEC, and had also carried out an Australia-wide study looking at possible sites for a centrifuge plant. This was done with the aid of consultants, but also involved staff of the companies. One important criterion for siting a centrifuge plant is seismic stability. Although to that time there was no experience on the effects of an earthquake on centrifuges, it was thought prudent to avoid any shaky site, which incidentally must have presented a problem for the Japanese. The two most favoured sites were one in South Australia, where the state government had long been interested in encouraging the establishment of the industry, and, as mentioned earlier, had its own study team led by Sir Ben Dickinson, and one in Queensland, just north of Brisbane at Caboolture. This was the favoured site, and it led to some opposition by local residents. It became clear that a serious public education campaign would be necessary, but all those involved had anticipated that. In fact, we began it by invitation with a public lecture debate in the University of Queensland, in which I debated with two anti-nuclear speakers who had some strange and inaccurate ideas of what an enrichment plant is all about. My feeling after that meeting was that we should be able to convince the opponents that their fears were unfounded. Those of us who had been associated with the AAEC's long-term interest in uranium enrichment were pleased with the conclusion reached by the UEGA. We had long since concluded that the gas centrifuge was the way to go for any future plant in Australia, and although we had no details of the big US centrifuges, we certainly knew enough about the technology to know that in this instance, big was not necessarily beautiful. It is worth pointing out at that stage the Australian state of knowledge on the prospects of the various technologies was probably better than anyone else's in the world, simply because between us we had seen and explained in some detail the technology used in all existing plants in the non-communist world, plus the new methods under development. So with the basis of the Australian uranium resources and the technical know-how already available from the AAEC, it seemed UEGA was in a position to negotiate an excellent deal for establishment of the industry here. The next step was to draw up the necessary agreements and contracts, and a start was made early in 1983. There would have to be two types of paper commitment. Firstly, contracts or agreements with the tripartite companies in relation to supply of technology, financing, marketing, and also future expansion. We would also press for agreement on supply of feed material from Australian uranium resources. And secondly, and most importantly, government-to-government agreements would be required between Australia on the one hand and the governments of the United Kingdom, Federal Republic of Germany and the Netherlands, covering the exchange and protection of technology. While most of it would be classified as commercial in confidence or similar, undoubtedly some would be secret, which is where the government came into the picture, particularly with its responsibility for international safeguards on uranium and its products. In other words, the tripartite governments would have to be assured of Australia's intention to protect classified information and the nature of the steps and procedures to be undertaken. And it was this requirement that led to the termination of the study. After the last round of discussions and negotiations in Sydney, the representatives of Centec Urenco returned home to draw up first drafts of the proposed documents. They were scheduled to return to Sydney to present and discuss these, when the Australian government changed from Liberal Country Party to Labor in March 1983. Soon after, in meetings with officials in Canberra, the word had passed to UEGA that there would be no government-to-government agreements relating to uranium enrichment technology from this government. Without such agreements, there could be no technology transfer. So once again, a change in government in Australia stopped dead the prospects of establishing a worthwhile industry based on upgrading our natural resources for export. The companies involved in UEGA certainly believed in the commercial prospects of the industry. There can be no doubt that Australia was in an excellent bargaining position to enter into very favourable arrangements for technology transfer and future collaboration, and for growth of Australian industrial participation at a rate commensurate with market conditions, thus minimising the risks of the large investments involved. As the demand grew in future years, the existence of our uranium resources would give solid justification for expansion of Urenco capacity in Australian plants as well as those in Europe and the UK. Commercial and marketing studies and predictions carried out by the UEGA and by the AAEC in support had shown potential annual export earnings from the enterprise to be in the range of $400 to $800 million by the turn of the century. And if the use of nuclear power grows, as I expect it will over the next few decades, these figures will become much larger. A useful contribution to Australia's balance of payments problems. but we preferred to forego it in favour of our misinformed political dogma. It is possible that the opportunity for technology transfer to Australia to establish a uranium enrichment industry may recur in the future, but I doubt we will ever have the strong negotiating position we had in 1982-3. We have destroyed our own know-how by closing down all research and development on uranium enrichment, and indeed on all aspects of the uranium fuel cycle, because of political ideology, in a country sitting on larger nuclear fuel resources than anyone else in the world. The consequences in the long term are hard to predict. I will look at possible scenarios in Chapter 20, but first a summary of the on-again, off-again story of the AAEC and uranium. End of Chapter 18.